All right, good morning, everyone. Let's get started. So just to let you know where we're at in the tentative lecture schedule, this week there is a problem-solving set on Friday, and it is a graded one, so it'll be very similar to the one that the practice one that we had last Friday, except we won't be taking it up at the end. You will just be handing a piece of paper in at the end. And just so you know, we are experimenting with a different grading platform, GradeScope, this year. We've never played with it before, but there are certain places where when we sign you into GradeScope for assignments, we're kind of not sure what's happening on your end of things. So you may be getting email notifications that something has happened in GradeScope. For this week, just ignore anything that comes your way as we try to learn about it. In the following weeks, I think that GradeScope will give you notifications when grades have actually been posted. I'm not quite sure. But anyways, more than likely something will come to you Friday afternoon after the problem-solving set. Don't get too worried about that. I think that will just be us loading you into the GradeScope platform, and then we'll give you more information about how to get access to your grades after the assignment's been graded. We'll also give you information on how to access the feedback, because I think we're trying to grade online in order to be able to give you more feedback on your written work. So fingers crossed this will help. And then of course with the student evaluations of teaching at the end, I will hope that I'll be asking you for very specific information about how GradeScope worked for you, just so that you can inform us as to whether it was good for you, what was bad for you, what was helpful, what wasn't, so we can do better in the following years. So all that to say is you might be getting some notifications by the end of the week. Ignore those, and then we'll recap once we know a little bit better what we're doing. Okay, so as far as material, something that popped out of the problem-solving session was the specific piece of information around the nodal cell action potential. So if you could just turn to this in your notes, I just want, for the sake of completeness, to make sure that everybody is clear that when we were talking about this post-repolarization refractoriness period, that was the period in which we were waiting, or the hypothesis is we're waiting for calcium channels to close. Okay, so let's just be really clear that in this range here, our voltage-gated calcium channels are closing in this region. Okay, so just to be super clear what that discussion was when we had it. Okay, so this does indicate that voltage-gated calcium channels don't close at a very specific point, kind of like we've seen voltage-gated sodium channels close over a very narrow range of time. Voltage-gated calcium channels take longer to close, hundreds of milliseconds to close. They close variably over that time period. Right, so that's where we got into that. If we could try to generate another action potential during the period where we're waiting for them to close, we're going to get something weird. We might get a bit of depolarization, but we're going to get something odd looking, because not all of them are closed yet. Okay, so just to be super clear, where in this process the voltage-gated calcium channels were closing. We think that's over that 200 millisecond period. Okay, that was just a piece that there were a fair number of questions around in the problem-solving set. So I just want to make sure we're clear. Okay, so then what we did last week is ended up thinking about the electrical nature of the heart, turning that into a contraction, right, which now turned it into a mechanical pump. And then we saw how that pump could actually change pressure as we compress against a volume. And then with a series of one-way passive valves, we can actually move volume from one compartment to another compartment. So we can move volume in through, if we're talking about the left ventricle or the left heart, we can move in from volume from the pulmonary veins through the left atria into the left ventricle, out into the aorta in a very directed manner, right? So now we've got a pump, which is pumping in a very, pumping our blood from one predicted compartment to another, right? So left ventricle, sorry, the left heart, remember, was in between the pulmonary veins and the systemic arteries, that aorta, and the right heart moving blood from our systemic veins up into the pulmonary arteries. Okay, so now we can get a very ordered movement of blood flow around the system because we created pumps. Okay, so now we're going to, and we talked a little bit about, let me just quickly check what we said. We talked a little bit about the output of the heart here. So we had a, I'm not going to write anything on here, just a review. We talked a little bit about the output of the heart then, because that's going to be very critical now. We talked about how at the end of diastole, right, so the heart has filled, or let's think about the left ventricle, the ventricle has filled with a certain amount of volume, and diastolic volume, the volume at the end of diastole, that's our preload, right? That's all we have to pump. Okay, you can't pump what you don't have. If you didn't fill the pump, you can't move volume out of the pump, right? So really critical for this pump is the filling piece. All right, so we fill with preload. We do that, we have that contraction, right, which means we ejected volume. So at the end of systole, that was contraction. At the end of systole, we've got a volume left over because we never empty the compartment down to nothing. Okay, there's always volume left in that compartment. So we have a volume at the end of systole. So the difference between the two was going to be what we actually ejected. Right? We called that stroke volume. So stroke volume was end diastolic minus end systolic volume. And classic numbers that we're going to throw around are end diastolic volume being 130 mils, end systolic volume being 50, stroke volume being about 80 mils. So 80 mils per beat gets ejected through that pressure-volume relationship that we looked at here. Okay, so now let's think about that cardiac output. Here. Let's think about that output of the heart, because that's going to be, game afoot is going to be trying to figure out what the cardiac output actually is. So if we think about the output of the heart, we talked then that per beat or per contraction, we're going to have a stroke volume. So that was end diastolic volume minus end systolic volume. So that was a volume we were going to move per heartbeat or per contraction. And now cardiac output is a volume measure over time. Right, so cardiac output, I'll write down that. So cardiac output is the volume that we move out per beat times the number of times your heart beats per minute. So times heart rate. So this is now a volume per minute. So at rest, so sitting there right now, you've got a cardiac, you're beating 80 mils per beat times, let's say, your SA node is going at 70 beats per minute. You're looking at approximately 5.5 liters per minute. Okay, so at rest, that's what your heart's doing. You only have about 5.5 liters of blood, so you are circulating your entire blood volume every minute that you're sitting there. Okay, so it's a good thing you're sitting down, you're working wicked hard. Okay, the system is pumping the entire volume every minute. Now during exercise, the system can change in a way, and we will look at how that might happen. The system can change in a way that you have an increase in contractility of the heart, which means you can eject more volume than you did before. So if we increase the contractility of the heart, the strength of the contraction, your stroke volume can actually go up to, let's say, 130 mils per beat. And if you're a fit individual, your heart rate will go up to about 180 beats per minute. Usually won't top out further than that, depending on your fitness level. So we can get ourselves to about 23 liters per minute. Okay, so during heavy exercise or maximum exercise, you can actually get your heart to circulating your entire blood volume approximately 5 times per minute. Okay, so this pump is working much, much harder, okay, in terms of its contractility per beat, as well as how many times it's beating per minute. Okay, so then the question is how do we go from here to here? Like, how do we control that cardiac output? Right, so what are the variables that are feeding into what cardiac output is? So if we ask, how do we do this? How do we control cardiac output? Well, you just look at the variables that make cardiac output up, all right, because nothing magical can be added other than what are the determinants of cardiac output. So we said cardiac output was derived by heart rate times stroke volume. And if we expand out that stroke volume piece a little bit, cardiac output is equal to end diastolic volume minus end systolic volume times heart rate. And so we'll work through a fair number of equations as we work through human physiology, but we're not actually going to work through equations to get an absolute number. We're using equations to actually just look at relationships, right? So if you look at this relationship right now, you could absolutely say, yeah, if I increase heart rate, I increase cardiac output. That's how they relate. If I increase end diastolic volume, I increase cardiac output. That's how they relate. Okay, so we're just looking at the equations to look at how things relate to each other so that then we can predict how one thing might affect another. Okay, so we're never going to solve equations for exactly what the number is. I don't care exactly what the number is. Mostly what we care about here is, can we predict whether something is going up or down? Because that's the critical piece, the directionality of it. Okay, so we're going to work on the basis of a lot of equations, but again, it's just to look at what the relationships are. So essentially, if we want to know what controls cardiac output, we got to know what controls end diastolic volume, we got to know what controls end systolic volume, and we got to know what controls heart rate. Done. Okay? So we're going to wander around thinking about these variables. So the variables are end diastolic volume, end systolic volume, and heart rate. So no big surprise, if we want to know how to control cardiac output, these are the things we're going to think about. And then essentially, why do we care about cardiac output? So it's important to know physiologically how we can change the system from 5.5 liters per minute to 23 liters per minute, but in relationship to where we started the course, right, in terms of thinking about negative feedback and that we were going to wander through the cardiovascular system thinking about mean arterial pressure, right? We care about cardiac output because it is one of the determinants, one of the variables that affect mean arterial pressure. So if we think about why, so just so you know where we're going or why we're even thinking about this, why do we care about cardiac output? Well, if we think about that aortic compartment, right, so we think about that cardiovascular system, and we talked about it being a functionally compartmentalized system, right? So each compartment is designed in a way that aids in the function of that compartment. So we talked about the systemic arteries being optimized for transport. We talked about capillaries. We'll get into those, optimized for exchange, et cetera, et cetera. So if we think about the aorta as a compartment, right? So if I've got this compartment that is connected to other things, so we can't just draw a box as this compartment because there's inputs to this compartment and there's outputs to that compartment, right? So if we think about the aorta, so one of our biggest systemic arteries, it's one of our first after the left ventricle. This is where we actually measure or monitor mean arterial pressure. So our body is set up to actually have sensors in that aorta in order to monitor what pressure is in that compartment, okay? And if we think about this is a compartment, then how do we fill that compartment and how do we empty that compartment will dictate the volume in it and the pressure in it, okay? So really when we think about what is mean arterial pressure, it's a volume in, volume out argument. We think about how's the volume coming in, how's the volume going out, what's the volume in it, and therefore what's the pressure in it, okay? So if we're thinking about flow in this direction, right, then how do we fill this container? We fill this container with cardiac output, right, because upstream of the aorta is the left heart. Right, so the cardiac output will be filling this container. If we increase cardiac output, we increase the volume in that container, we increase mean arterial pressure. Okay, if we decrease cardiac output, we'll be decreasing volume into that container, decrease it in volume in it, decrease pressure in it. Okay, and that's what the body's set up to sense and set up to control. Okay? If we think about what's downstream, how do we empty this compartment? What's downstream of this is a set of resistance arterioles, so things that we can constrict and dilate. So we have huge control over volume coming out of this compartment. And when we will wander around the vascular system a little bit more in order to clarify this, but now you can vasoconstrict, right, which we make an increase in resistance here. If I were to increase resistance right here, I'm going to get a decrease in volume out of that compartment. And if I get a decrease in volume out of it, there must be more volume in it. If there's more volume in it, there's more pressure in it. Okay, so again, and then conversely, if I vasodilate, and I drop resistance here, and I get more volume out of the compartment, I'm going to have less volume in that compartment, less pressure in that compartment. Okay, so the game afoot in terms of mean arterial pressure is a volume in, volume out argument. Okay, cardiac output is part of the volume in side of the thinking. Okay? So again, the body is concerned about that compartment in particular, where if we measure an increase, if we get an increase in volume, that's going to lead to an increase in pressure. If we get a decrease in volume, we're going to get a decrease in pressure. Now notice I never talked about flow through the compartment. I don't care. I don't care about what flow through it is. I care about what volume into it is and what volume out of it is. So I can predict what's in it and what pressure is in it, okay? Don't necessarily care at the moment about flow through. Okay, so this is why we care about cardiac output. We're going to think about how do we control cardiac output. We're going to wander around thinking about these three things. Okay, so that's where we're headed next. We're going to think about what dictates end diastolic volume, what dictates end systolic volume, and what dictates heart rate. Okay, we've already touched on that a little bit. You already know how to control the SA node through the sympathetic nervous system and the parasympathetic nervous system, right? So we're gonna revisit that for sure, as well as some other issues. Okay, so that's where we're headed. let's, where did my paper go? Here it is here. Okay, so let's think about end diastolic volume. This is going to be a slightly shorter discussion because end diastolic volume is dependent on what the veins are doing. And we've got a lot of wandering around the cardiovascular system before we get to the venous side in order to understand how we're actually filling the heart. So let's think a little bit about end diastolic volume for the moment, and then we're going to kind of put a pin in it, hang on to it, and then probably about 4 days come back to this. Okay? So we have talked about end diastolic volume as our preload. It's the volume in the ventricle just before systole. Or just before contraction, okay? And it actually is a representation of the blood returned to the heart from the venous side of the system. If we're talking about the right heart, it's superior and inferior vena cava. If you're talking about the left heart, we're talking about the pulmonary veins. So it really is the blood returned to the ventricle so it is veins are dependent on veins or venous function. Okay, so we really do have to know what the veins are doing before we can return to thinking about end diastolic volume. Okay, so let's leave that as a placeholder, but it is true that end diastolic volume is actually going to affect end systolic volume. So if we think about our second variable that we wanted to talk about, end systolic volume, end diastolic volume, whatever it is, because of whatever the veins are doing, will affect end systolic volume directly. And so just to write down how they are related, remember we had our numbers, end diastolic volume was about 130 mils, and systolic volume was about 50 mils. So our stroke volume was about 80 mils. Okay, and that was under our normal conditions. It is true, this is how the heart functions. If you were to increase end diastolic volume, the heart will pump harder. Okay, so if we were to increase end diastolic volume, the heart will pump harder. We will actually drop end systolic volume because it pumped harder and increase stroke volume. Okay, that's part of how the heart works. So let's write that down. So if I increase end diastolic volume, that's going to result in an increase in contractility of the heart. Or an increase in contractility of the ventricle, right? That is an increase in strength of contraction of the heart. And if we contract harder, we will eject more volume per beat. So we will increase the volume ejected from the heart. So essentially, what I've written here is if we return more blood to the heart, we eject more. So end diastolic volume affects end systolic volume and affects stroke volume. Okay? All right, so let's look at how that's going to work. Okay, so we're going to jump from this discussion, leave an end diastolic volume discussion until we tap into the veins, and we're going to pop into thinking about that end systolic volume. How did end systolic volume get changed by end diastolic volume? Okay, let's pop into that. Okay, so a discussion on end systolic volume. Okay, so let's just transfer this over here so we remember what we're talking about. End diastolic volume minus end systolic volume. Okay. So, end systolic volume, if we increase the strength of contraction of the heart, so think about where we're at, think about what this variable is, we're going to increase the strength of contraction of the heart, right? We will have ejected more volume, which means end systolic volume has dropped, right? So an increase in strength of contraction of the heart drops end systolic volume because we pumped it out. Okay? So an increase, let's just write that, increase in strength of contraction will result in a decrease in end systolic volume, which will therefore increase stroke volume, right? So if I drop this, stroke volume has to go up. And because cardiac output was directly related to stroke volume, if stroke volume goes up, therefore we get an increase in cardiac output. Okay, and from then the little volume in, volume out argument we just had, we would predict that would increase mean arterial pressure, right? What's happening there? Okay, so why is this happening? So this is an intrinsic regulation of the heart. So that means it's a relationship or a regulation that originates because of the nature of the tissue itself, right? It's not an influence coming from outside. So the sympathetic nervous system or the parasympathetic nervous system coming in to influence heart function, that would be considered extrinsic. It's influence coming from outside the piece of tissue affecting that piece of tissue. Intrinsic regulators are things that are happening within the tissue itself, okay? So this intrinsic regulators are regulation by a factor originating from within the tissue. All right. So there's a few intrinsic things happening within the heart. The first is the Frank Starling, oh, disrespected him there, capital S. Frank and Starling were two researchers that discovered the heart working in this way. And what they found was if they looked at end diastolic volume of the ventricle, that if they increased the end diastolic volume, they would increase the stroke volume. So that's really just the sentence exactly what I wrote out, right? That's really just what this graph says, right? If I were to increase the end diastolic volume from normal, so here's our normal scenario. We've got an end diastolic volume of 30, right? And when we have an end diastolic volume of 30, that relates to a stroke volume of 80 mils. Okay, perfect. So we know that relationship, right? We've seen that. And now they would argue if we were to increase end diastolic volume, let's say, I don't know, to something above 130, okay, that will result in an increase in stroke volume. Okay, so this graph is just saying what I've said in words. It's just showing you the data. So essentially, why is this occurring? So this is just, they've just, don't try this at home, they just took the heart out, they filled it differently, and they saw that when they filled it, it contracted harder, okay? It contracted with more force. essentially what they were doing was by increasing an end diastolic volume, they were stretching that container, right? That ventricle is like a small container, small sac, and when you fill it with more, stretch it a bit more. Fill it with more, stretch it a bit more. Okay, so they did note that end diastolic volume is actually stretch, right? And then stroke volume, why did we get an increase in stroke volume? Because the thing contracted harder. It contracted with more force. Right, so not only is this a relationship between end diastolic volume and stroke volume, it's a relationship between stretch and force. Okay, so what is happening? When you stretch cardiac tissue, you get more force. Okay, so what is happening here? So we've seen a similar phenomenon like this in skeletal muscle, so from Human Phys 1. Does anybody remember the relationship between stretch and force in skeletal muscle and what that might look like? Remember that? Might have referred it to, rather than referring it to as stretch, it might have been sarcomere length. Right, and as you change sarcomere length, you got different forces. Do you remember that relationship? So tension or force, commonly referred to as the length-tension relationship in skeletal muscle. Let's make sure we're here. Okay, so in skeletal muscle, if we have really short sarcomere lengths, so you have a muscle that's really short, you're not going to generate much force. Okay? And so and again, this is just experimental data, as they pull that muscle out, as they stretch that muscle, they pull out each of the sarcomeres, so the sarcomeres are becoming longer, then force will go up. Right? And then there'll be a period where it tapers off, force doesn't go up anymore. And then as you continue to stretch it and stretch it and stretch it and stretch it, force will actually drop. Okay, so you get this classic length tension curve in skeletal muscle. Do you remember why that was? Or can you think now of why that would be? Yeah. Perfect. So you described this end of it and this end of it, right? So if we think about that sarcomere where we have our actin and our myosin, and we're required, the myosin heads actually interact with the actin molecule. And if we have a sarcomere so stretched out that the myosin heads can't interact with the actin, in this case, you can't generate force. Right? And conversely, if they're so jammed up with each other, like let's say I've got my Z lines and my little actin, and then my actin and my Z lines, and they're crashing into each other, and then I've got my myosin here, and they're crashing into each other, yeah, it's now very difficult to shorten that sarcomere because the proteins are interfering with each other. Right? So we go from this, where we're not generating much force, and we pull it out. Right, and as we at some point, as we lengthen and we test force and lengthen and test force, we're going to come to an optimal length, right, for force generation, right? So in skeletal muscle, this is how we're built. Okay, so every muscle is built to operate in that optimal region. Okay, so for instance, my bicep, I cannot get my body into a position that's healthy that would make that muscle go too short or too long. I can go a little bit shorter, and then go a little bit longer, but I can't get myself here. We're just not built that way, okay? So our muscles, our bodies are actually built to get our skeletal muscles into positions where we can get an optimal length for force production. Okay, so we're built this way. Okay, so the heart is also, it's muscle. Cardiac myocytes, they have sarcomeres, right? So a similar thing is happening here. When we fill the heart chamber, right, we're going to set the sarcomeres at a certain length, and we're going to get a certain amount of force generated when the action potential comes to cause contraction. If I fill it more, if I increase my end diastolic volume, if I fill it more, I start to stretch out my sarcomeres, right? If I fill it less, my sarcomeres will be shorter, right? It just so happens that the heart does not live, or we do not live with a heart that is at optimal length for its sarcomeres, okay? So the length in terms of fiber length and force generation, so this is the length tension relationship in the heart. Okay, so this is our heart length tension relationship, right? We live here. That's where we live under normal conditions. So now if we were actually to fill it more, increase our end diastolic volume, we're actually going to get more force. Okay, so the length tension curve is the basis for the end diastolic volume stroke volume curve. It's actually just a length tension curve, but in heart speak, okay? Because now we're talking about a chamber, we're talking about we change its length by volume, right? And then we look at force. How do we measure force, stroke volume? Okay, so these are exactly the same things, okay? So essentially, what we're saying is, because we don't live at the optimal part of the curve, that I do have the opportunity to fill it more and get more force. And then I could fill it more and I could get more force. And I could fill it more and get more force. Okay? So that's just going up and up and up by increasing end diastolic volume and getting more and more and more stroke volume. Okay? We are just optimizing actin-myosin overlap in the heart. That's all we're doing here. So this is why it's called intrinsic control. This is just how the heart is going to operate. This is how the thing is structured, and it's just going to function this way. There's no way to stop it from doing it. Okay? If you get more back to the heart, there will be an increase in contractility, and we will get an increase in stroke volume. Okay? So there is a limit to this, and in fact, so we do plateau, kind of like we did with the length tension curve in skeletal muscle. We do plateau, sorry. And in the body, this is limited by the pericardium. So we do have a heart that's encased in a very fibrous sac. So we can only fill it so much, okay? It can only stretch so much, and that's a very good thing. Okay, we don't want to be able to stretch the ventricles out too much, depending on how much our volume we return back to the heart. Okay, so this is limited by our pericardium. Experimentally, though, if you were to remove the pericardium, so again, don't try this at home. If you were to remove the pericardium and continue increasing end diastolic volume, you will end up being able to express the decrease in force because the sarcomere length is now way too far. Okay, so you can only get at this experimentally. We haven't evolved in a way to allow us to get out onto this branch of the relationship, right? So we've got a pericardium in there to help us out. Okay, so this is how end diastolic volume is going to affect end systolic volume and therefore affect stroke volume. Okay, so they're intrinsically related to each other because of how the heart's set up. Okay, are we good with that relationship? Length, tension in the heart. Thank you, Frank and Starling, for all your dedication. Good? Okay, so there's a second intrinsic relationship in the heart, which is one that is quite interesting. So this is a second intrinsic. Yep, that's right. Or second intrinsic regulator. So we'll see this known as this, it's been called the staircase phenomenon. Not related at all to that weird documentary. Have you ever seen Netflix, The Staircase? Has anybody watched that? Oh, I think he's guilty. I don't know. But it's not related to that, but that totally creeps me out. Staircase phenomenon, it's also some places will call it TREP. The TREP phenomenon. Okay. And this is a phenomenon where if we increase heart rate, we increase the force of contraction. Okay, so for example, the data would look something like if we were plotting force over time, and we were, let's say, we were just plotting, or we had a certain heart rate, okay, and that, let's say one of these indicates a heart rate over time. And then suddenly we were to increase the pacing of that heart. Okay, so let's say it's externally paced, so suddenly we were to increase the pacing. The force will step up and go to a level that is related to the pace. So the greater the pace, the greater the force. Okay? And then if you were to drop the rate back down to normal, it drops back down to normal. Okay, so you get an increase in force when there's an increase in heart rate. So therefore, if we get an increase in the frequency of contraction, you get an increase in force developed. I get an increase in force developed. I drop my end systolic volume, right, because I ejected it out. Where is it? It's in the form of stroke volume. I increased my stroke volume, and that would increase my cardiac output. And now you can follow what that would do to mean arterial pressure. Okay? Now the mechanism for this is, we have no idea. Okay, so this is a get to grad school moment. Come back in 10 years and tell me all about it. So we have no idea what the relationship is here. Why? And think about the mechanisms, right? Heart rate is just an action potential frequency increasing, right? But we did know that, or we did talk about like all of those effective refractory periods, they all shortened up. So the channels were doing something a little bit different when rate went up, something that we wouldn't have predicted. So again, somehow that is translating into possibly an increase in calcium in the cell, which would increase force, right? That's the only way we're going to get an increase in force in that myocyte. So if we're talking about that ventricular myocyte action potential that we talked about, that plateau region increase, or where we open voltage gated calcium channels, that was trigger calcium. That was associated with force. So if we were thinking about going to study this, that's probably where we'd go first, right? We'd go look into that channel and see to do more open when heart rate increases and what caused that, right? So once we know the mechanisms or the things like from their building blocks up that helps us zone in on when we can't figure out what's going on. It helps us zone in on, well, where might we look? Okay? Because we can narrow it down here. Okay, so two intrinsic regulators of ways in which either end diastolic volume will affect stroke volume or contractility, and heart rate affecting end systolic volume, stroke volume, and contractility. Okay, so two intrinsic regulators. The heart's just going to do it. Okay, we can't stop it from doing it. But then we have extrinsic regulators. So this was that nervous system that we talked about, right? So when a piece of tissue is regulated by factors originating outside of it, okay, that's extrinsic. So regulation by factors originating outside of the tissue. So one piece of tissue communicating with another here, okay? So the nervous system communicating with myocytes in this case. Okay. So we have thought about the sympathetic nervous system and how it innervates nodal cells to change heart rate, okay? We also have direct sympathetic nervous system and parasympathetic nervous system innervation into ventricular myocytes themselves. Okay, so there are two spots where the sympathetic nervous system and the parasympathetic nervous system come in to regulate the heart. SA node and the myocytes themselves. Okay, so we have direct innervation of the cardiac myocytes themselves. So we have sympathetic nervous system releasing norepinephrine, as it always does, right? So if it's releasing norepinephrine onto a cardiac myocyte, that cardiac myocyte has to have an adrenergic membrane receptor population. Okay, is it alpha or is it beta? In this case, it happens to be a beta adrenergic membrane receptor population. If it had no adrenergic membrane receptor population, the myocyte would not even know norepinephrine is out there. Okay, so it's critical in the communication between these two pieces of tissue. So that beta adrenergic membrane receptor turns on a stimulatory G protein. So we've got a G protein step. We increase an enzyme. So this is our classic second messenger system. We increase an enzyme, adenylate cyclase, to increase a second messenger cyclic AMP. Okay. Classic communication through second messengers between two pieces of tissue. So that increase in cyclic AMP is going to increase protein kinases, and we're going to start phosphorylating stuff. So we're going to start throwing phosphates onto things all over the place. Okay? So what are we going to do? We're going to phosphorylate a voltage-dependent calcium channel. So there are voltage-dependent, so we're not myocyte, remember. There are voltage-dependent calcium channels that don't open during a given action potential unless they're phosphorylated. So we add a phosphate onto them and boom, now they open. Okay, so there's a phosphorylatable group of voltage-gated calcium channels. So when we have an increase in cyclic A, we have an increase in protein kinases that are phosphorylating these voltage-dependent channels. We're now going to get more channels open per action potential because we recruited this new group. The old group is still there, but we recruited this new phosphorylatable group. Okay, so if we have an increase in number of channels that open per action potential, right, so we're up now, we're on that plateau of our action potential, that was trigger calcium coming in. Now we've got an increase in trigger calcium coming in, an increase in calcium in a myocyte. Okay, that should trigger something. An increase in calcium in a myocyte is going to cause, through lots of different steps, getting actin and myosin together, which is what all the ... means, because we're not going to go through that, but you're going to result in an increase in force of contraction. More actin and myosin got together, more force. Okay? I'm also going to, we have pumps on the sarcoplasmic reticulum that then end the contraction, right? So those pumps actually take the calcium up and put it back in the sarcoplasmic reticulum. and those pumps take the calcium out of the intercellular space and pump it back to the outside, right? We can actually phosphorylate pumps on the SR, increasing their activity and increasing our speed of contraction. Okay? So a myocyte exposed to norepinephrine is going to contract harder, and it's going to contract faster. Okay? So if we think about a myocyte generating force over time, under normal conditions, it's going to generate force based on that calcium, that trigger calcium coming in during the action potential. So this is under normal conditions. Under the influence of norepinephrine, I'm going to contract harder, so increase contractility. And once the calcium is in the intercellular space and we're getting contraction occurring, the sarcoplasmic reticulum pumps are taking it out real quick. So it's going to contract faster. So we get rid of that calcium quicker. So this is a muscle on beta stimulation or exposed to norepinephrine. From the sympathetic nervous system. So this is going to be our nervous response. To norepi. Okay, let's take a break before we look at what the parasympathetic nervous system does. So back at 9:30. Okay, everyone, let's get back to thinking about our little cardiac myocyte here. So this is, we contract harder and faster because of voltage-dependent calcium channels and pumps on our sarcoplasmic reticulum that are all phosphorylatable in some way, right? So we can change their activities. And so a myocyte exposed to norepinephrine is going to contract with more force and is going to contract faster. The myocyte exposed to acetylcholine now, so if we think about the parasympathetic nervous system, right, the parasympathetic nervous system releases acetylcholine, as it always does, onto the cardiac myocyte. So there has to be a membrane receptor population there for the acetylcholine. So we have a cholinergic membrane receptor population sitting on the myocytes. If it didn't have it, acetylcholine, the myocyte wouldn't even know the acetylcholine is out there, right? So we have to have that critical communication step. Got to have a membrane receptor. That's going to stimulate an inhibitory G protein, all right? When we were stimulating with norepinephrine, we stimulated what's called a stimulatory G protein. Now we're stimulating an inhibitory G protein, which decreases an enzyme, adenylate cyclase, decreases the amount of the second messenger. So we decrease cyclic AMP. We're going to decrease the activity of our protein kinases, and we're going to stop phosphorylating or decrease the phosphorylation state of things. Okay, so we actually do now the exact opposite. Okay, so if we're decreasing the phosphorylation state of things, we're going to decrease the number of phosphorylated voltage-dependent calcium channels. We're going to open fewer channels per action potential. We're going to get less calcium, and we're going to get a decrease in contractility. It's the opposite of this argument. Okay, so it's just the reverse of this, because the reverse happened. Increase adenylate cyclase, decrease adenylate cyclase. Okay? Increase phosphorylation states, decrease phosphorylation states. So it's the exact opposite of the argument. So at the end of the day, we're going to affect voltage-dependent calcium channels and then result in a decrease in the number of channels open per action potential, decrease our trigger calcium, and ending up decreasing contractility. Okay. So work to reverse these arguments, okay, so they make sense. Similarly, target site is going to be those calcium pumps on the SR. We're going to decrease their activity and decrease the speed of contraction. Okay, so again, it's just the exact opposite of the argument up here. So we're going to end up decreasing our speed of contraction. All right, so if we think about force over time, we're actually going to have less force. Let me make sure we get it here. Less force for longer. Okay, and so this is when we stimulate cholinergic membrane receptors. And the stimulus here would be the parasympathetic nervous system. Okay, so it's a nervous response. The nervous response is important to think about because that's speed, right? We can do this very quickly. If we're taking the energy to connect the brain to the cardiac myocytes, this is something that we can do very quickly, on the order of milliseconds to seconds, okay? And the critical is this, very purposefully I've put beta stimulation on for when we increase force and cholinergic stimulation on for when we decrease force, because it doesn't matter what stimulates that membrane receptor, that same thing is going to happen. Right, so for example, if I have a nerve releasing norepinephrine right beside a beta adrenergic membrane receptor on a myocyte, that is going to happen. Okay, but if I have a sympathetic nervous system which is stimulating my adrenal glands to release epinephrine and norepinephrine into the bloodstream, and those hormones find the membrane receptor population on the heart, that exact same thing is going to happen, okay? The beta membrane receptor has no idea how it's been stimulated. It just knows it's now occupied. Whether that norepinephrine came from a nerve or that norepinephrine came from as a hormone circulating in the blood, it doesn't care. It's just doing what it's told. Okay, so it doesn't matter how it got occupied. That will happen, okay? So we talked about intrinsic control, we talked about extrinsic nervous control, and now we're talking about extrinsic hormonal control, okay? Because we're talking about all the same machinery, the norepinephrine and epinephrine just came from a different place, okay? So extrinsic hormonal control, sympathetic nervous system, stimulating the adrenal glands, releasing epi and norepi, and of course they're releasing this into the bloodstream. Okay, so this is our hormonal system. Okay, that is now going to circulate in the blood. We know we circulate our blood at rest 1 time per minute, right? So it might take a minute for those hormones to find the membrane receptor population on the cardiac myocyte, binds to an adrenergic membrane receptor population, and the results will be exactly the same as sympathetic nervous system stimulation. Okay, the results will be exactly what is downstream once you stimulate the beta adrenergic membrane receptor population. All right, so the results. Will be the same. As sympathetic nervous system stimulation. Okay, so back over on this graph, we can add, not only can we get this more force with over less time from the sympathetic nervous system, we can also get it through epinephrine and norepinephrine through the hormonal, as a hormonal response. Because we're putting that hormone into the blood and letting it circulate, and then it's got to find its membrane receptor population. It's going to be a little bit slower. Okay? So it's often thought that the hormonal response, because that's going to be a seconds to minutes response, that nervous response is going to be milliseconds to seconds, right? So we've got a couple of time scales now in which we can activate a piece of tissue. And normally they act in series with each other. The nervous system will immediately affect the heart because it's directly connected. So within milliseconds, we can change the force of contraction. As the sympathetic nervous system then is also directly connected to adrenal glands releasing epinephrine and norepinephrine, so that this norepinephrine and epinephrine can find the membrane receptor population to do exactly the same thing. So the sympathetic nervous system control over the heart can back off a little bit because now we have hormonal support on board. Okay, so we don't need to busy the heart busy the brain all the time with all this control. Sometimes we hand things off to the hormonal level. Okay, so they often support each other instead of add to each other. But we got both on board. There is no hormonal acetylcholine. Okay, so if we're going to turn it down, we don't have a place where the parasympathetic nervous system goes into a gland and releases acetylcholine into the blood and then finds a membrane receptor population. Can you think about why that might be? Why we wouldn't use acetylcholine in the same way as we might use norepinephrine? Think about how we contract muscle. Right? Do you remember how we contracted muscle? The neuromuscular junction. What did we use at the neuromuscular junction? Acetylcholine. So what does every skeletal muscle cell in your body have? A cholinergic membrane receptor. So if we put acetylcholine out into the blood, you just might randomly be stimulating stuff, right? We can't have that happen. We can't have that happen, right? So acetylcholine doesn't show up as a hormone because of how some of the other cells are actually put together or how the other systems are put together, right? So we will not find acetylcholine wandering around the bloodstream as a hormone. It would be funny to walk down the street that way, but a little catastrophic. Okay, so what do we got here? We've got hormonal control. We've got some paracrine control. So we have some cells that hang out nearby cells of the heart, right? Anytime you're going to get paracrine control, they need to be neighbors. They need to be living beside each other. They need to reside near each other because they're just going to be using diffusion as a way to communicate, right? So we do have endothelial cells that line the entire cardiovascular system, which means they also line the inside of the heart. So the heart is lined with endothelial cells. And they release products. So, for example, they can release endothelin. And they have a membrane receptor population. So we have endothelin 1 and endothelin 2 membrane receptors. They use the second messenger IP3. This is all we know really so far. We use uses the second messenger IP3, increases calcium available for contraction. And we don't really know how that works. That's all we've got so far. Endothelial cells releasing products was really only discovered in 1980. So it's like discovering an entire new organ in the body that we'd never known before. So between 1980 and now, they've been discovering all these different products that endothelial cells release to help control the cells nearby. I've never gotten a phone call in the middle of a... It might be for one of you. Oh, really? Oh, it won't go. Okay. We'll leave it down there for now because we're busy. All right, we be busy. They're probably like, the front of the building's on fire, get out. And I'm like, nah, talking about endothelin. Leave us be. Okay, so we got endothelin, a product of endothelial cells, also nitric oxide. Nitric oxide is a product of endothelial cells, and the data here are really a mixed bag. The effect of nitric oxide on cardiac myocytes have been shown to increase force or decrease force depending on the situation. So a really confusing set of literature here on what does nitric oxide do to the heart and how does it affect it. So again, this is our get to grad school moment. Okay, and then, so these are like cellular influences, and then we have some pressure, volume influences on end systolic volume. Remember, that's what we're talking about. We're talking about end systolic volume, right? Controlling end systolic volume. So if I have a high afterload is the volume and the pressure in the aorta. Okay, so we're talking about the left ventricle here. So we have a high afterload. We're going to decrease, right? So we're going to decrease the amount of volume out per contraction. Do you remember a contraction delivered by the action potential is a timed piece of thing? It's a timed unit, right? So if we spend more time in that contraction cycle trying to open up the aortic valve, we have less time to eject volume, right? There's only a certain period of time during contraction. Systole is a timed event, right? So let's say we have 500 milliseconds in terms of how long we're in contraction. The afterload will be dictating how long of that 500 milliseconds are we ejecting volume. And that is dictated by how quickly we can get that aortic valve open. If afterload is high, we're going to spend a lot of time trying to get it open and then less time ejecting volume. If afterload is low, we're going to get it open very quickly and spend less time getting that valve open and more time ejecting volume. Okay, so the afterload is now going to be dictating how much volume we can get out because of how much time we spend being able to eject volume. So the high afterload will decrease. So let's say I've got the high afterload, it's in the aorta, we're talking about the left ventricle. I'm going to decrease my volume out per beat. Right, if I drop the volume out per beat, where is that volume? Right, if I didn't pump it out, it's still in the ventricle, right? If I didn't, it's not out there as stroke volume. So if it's still in the ventricle, I'm going to have increased my end systolic volume. So at the end of systole, I've got more volume in there because I didn't eject it, which will be a decrease in stroke volume and a decrease in cardiac output, and therefore a decrease in mean arterial pressure. Okay? And the reverse of that argument is completely true. Low afterload. We should be able to open that valve, the aortic valve, earlier. Increase our volume out. If we've increased our volume out, we have less in the ventricle, so we should drop our end systolic volume, increase our stroke volume, increase our cardiac output. Okay, so that argument is completely reversible. Okay, so we've talked about end diastolic volume as a variable dictating cardiac output, and systolic volume and how we control it as a variable of cardiac output. And then the last argument is to think about control of heart rate. So So we'll just start that argument here. I know we're right near the end, but if we're thinking about heart rate, how do we control that? We've already been here, right? This is information you already know. Parasympathetic nervous system stimulation of the SA node, and you know a whole lot more about that than I've written here. Okay, so go back and review the notes as to where we had parasympathetic nervous system stimulation of the SA node. Likewise, sympathetic nervous system stimulation of the SA node. Added on to here is we also innervate directly the AV node. Right, so the AV node does actually, or is actually innervated. Okay, and if I've got a membrane receptor population for norepinephrine on the SA node, then I've got a way to control it hormonally as well. So I've got neural and hormonal control over heart rate. Okay, but that's nothing new. Okay, we'll continue this on Thursday.